All right, Noetherian rings. So we want to know, is Noetherianity preserved under subrings and under quotients? The short answer is no and yes. The long answer is no and yes. The longer answer is we actually prove these. So let's see here what we're going to do. The first thing this should be sort of, you should sort of expect this answer, because the general idea in rings is that, well, first of all, in terms of like, is it preserved under subrings? Just in general with rings, subrings do not behave nice. They're not really nice. They don't tend to act nicely. Like, it's hard to say like, oh, this thing, here's this really nice thing about rings. Does it hold for subrings? Generally, no. Generally, you should not expect subrings to be nice just because a ring is nice. Now, ideals are really nice. And so if you quotient by an ideal, then you should expect good things to happen. Now, particularly since ideals are naturally the kernels of homomorphisms of rings. So, yeah, you should expect that. Oh, you look at a subring, oh, you shouldn't expect something nice. Oh, you look at a quotient, you should expect something nice. So, for a subring counterexample, and I'm not going to, by this, of course, I mean, and for an example of a ring with a subring such that the ring is Noetherian and the subring is not Noetherian, that's a lot of words, so I'm just going to write this. So for a subring counterexample, consider the ring R is just F adjoin countably infinite aleph null many variables x1 x2 all the way to infinity, where F is a field. Let's see here. So what is this? This ring consists of, let's see here. Actually, I'm not even going to write it out. I'm just going to explain what it is. Basically, what it is that you take polynomials, but instead of being in, actually, no, I will write it out. R consists of polynomials in let's see here. Polynomials in finite subsets of the variables 1, x1, x2, etc. So basically what you do is you choose, for any element of R, you choose a particular finite subset of this collection of variables, and you can take, and this is of course with coefficients in F. So what you're doing is you're taking polynomials that use only finitely many of these countably many variables that we're joining to F, and you can take them to different powers, and you can like multiply them together. But basically, you're building polynomials, and so of course the polynomials, each polynomial has finitely many terms, and each term consists of some constant in our field F times some product of these polynomials but you can only take a product of finitely many polynomials. Or no. A product of finitely many variables. So, and those finitely many variables, they could be raised to different powers, but you can't. Yeah, you can raise them to different powers, and that's fine, but you can't multiply a countable number or an infinite number of variables together in any particular term. And of course, there are only countably many terms. So basically, this isn't like formal power series in any sense of the word. There's no, you don't deal with infinity here. This is a very, even though you're joining infinitely many elements, you don't really see that through any one particular polynomial. No particular polynomial includes a infinite number of distinct variables. Anyways, so that's enough of rambling on what f adjoin countably many variables is. So I claim R is a domain. Okay? To prove this, let f and g be in R be such that f times g equals 0. See here, since f and g since the variables included in the terms of, actually, this is a lot of words. Let's use some symbols. We can write f as the sum overall, let's see here, sum overall alpha So we're going to take a multi-index new in parentheses, and no, let's make this like a vector. Let's call it v, but it's not really a vector, but sort of is. This is going to be in, let's see here. So this is going to be in, what we're going to do is we're going to take a sub v, and then we're going to take x to the power of v, where x is equal to 1, x1, x2. I don't like that. Let's make this 1 equals x0. So we're going to have x0, x1, and v is going to be some power, and a lot of these are going to be zeros. So what this really is it's because it can include 0, it's going to be omega to the n. And this is probably horrible notation, but omega is a notation I've seen for the collection of positive integers including 0, so non-negative integers, because some people think n includes 0, some people think n, boldface n of course, some people think boldface n includes 0, some people think it doesn't. I'm of the opinion that 0 is not a natural number, and so when I say this natural number here, basically what that means is we have countably many elements. It's a countable product of elements of omega. And so basically what this is, x to the v, but v is only allowed to be see here. You know what? This is really, I'm not quite sure what the best way to write this out is, because I didn't really I never really talked about adjoining countably many variables in class. And so when I first saw it, I was like, oh, so maybe this ring R could include, like, say, the polynomial sum from I equals 1 to infinity of xi. But it turns out that's not allowed. That's not an element of R, because it's because it has countably many xi's. And of course, like, similarly, you can't have, like, the sum from 1 to infinity of x2i. That also would not work, because you have countably many as well, even though you're not hitting all of them. You're missing countably many, but you're still including countably many. But anyways, so I kind of picked all this stuff up on my own, and I'm sure if you read about it, there's, like, some way, like, oh, here's how you talk about elements of f adjoin countably many variables. But I mean, I don't know. And it's not that, like, things like this, I think you can make a ring out of it. I was talking to someone about this, who seems to think that there is a way to do it. And it's sort of like how you can, when you consider polynomials, you only consider polynomials of finite degree, but you can actually talk about the ring of formal power series, and it turns out that the ring of formal power series is actually a ring. So anyways, huge dialogue aside, what I'm going to say is, then there is some natural number and an n such that f and g both belong to f x1 through xn. Wow, my laptop is really heating up, and it was going really slow on the last video, and I'm a little worried that it's not going to be picking up a lot of this video, but we'll see what happens. So anyways, so we can choose, because the reason that I'm saying this is that f and g, that elements of R use only, remember I said they use only finitely many variables in our countable collection of variables, and so for each of them, if you go out far enough, then you'll have included all of the variables that are used in that particular element of R. And then you choose n to be bigger than whatever the biggest of the two is. And so what you can do is you can view f and g as elements inside f adjoin just finitely many variables. And this is good, because we know already that for any field f adjoin finitely many variables is a domain. So fg equals 0 implies that f equals 0 or g equals 0. And this holds for all f and g in R, and hence R is a domain. Okay, so there we go. So now we know that, so this is big. We now know that R is a domain. So also R is not Noetherian because the proper ideal chain, I guess I say proper ideal chain a lot. I guess that's not really necessary. X1 is contained in the ideal generated by X1 is contained in the ideal generated by X1 and X2, contained in blah blah blah, does not stabilize. I.e., you do not eventually get the same, it does not eventually reach some ideal and then stay there for the rest of the sequence. Okay, Now, why did we need to have this be a domain? Because basically, what the strategy here to do is, instead of like, what one thing you could think is like, oh, let's try to think of a ring which has a subring that is not Noetherian. And that's a little tricky to do. I think you can do it, but this seems a lot more natural, because all you need to do here, you know what, now that I think about it, we don't need this here. All we need to do is find, what we're doing is we're actually starting with a subring, we're starting with a ring that we know is not Noetherian, and trying to find a super ring which is Noetherian. And the reason that we need this to be a domain is because we're going to make a field of fractions. And you can only make a field of you can make a field of fractions only with a domain. And then once you make the field of fractions, then you have a field, and those are very easy to show that they're Noetherian, because because you've only got two ideals. So there's the ascending chains are pretty boring. Okay, so let's write that all out. Since R is, I've basically outlined the rest of this particular counterexample. Since R is a domain, we can obtain the field of fractions of R by localizing at Rx to not obtain, but obtain a field which we will call FR for the field of fractions that we get from R. So FR has just two ideals, and so it is Noetherian. Hence, FR is an example of a Noetherian ring with a non-Noetherian subring. Because remember, when we make the field of fractions, we have that natural homomorphism going from the field of we have a natural homomorph. Basically, we have the original ring R naturally embedded in FR by you just map every element of R to the element R over 1. And that's how, and so we get this, so you get this other ring, and it's all nice. Everything's nice. Well, it's nice in the sense that this proof works out. It's not nice in the sense that you have a non-Noetherian subring of a Noetherian ring. You know, I guess when I say it's not nice, it's like it is precisely what it is, because this is math and that's how that works. And if it were nice, then it wouldn't be what it is, if that makes sense. But anyways, this is what we wanted. We wanted either a proof that the statement was true or a counterexample to the statement. And we found a counterexample. We found a Noetherian ring with a non-Noetherian subring. Okay. So let's do the next part. So next, let R be Noetherian. I'm just going to write N. And I an ideal in R. I'm going to use this notation, the same inclusion notation that we use for normal subgroups. And that makes sense because normal subgroups are to groups what ideals are to rings. They play the same role, i.e. they are the kernels of homomorphisms of the respective categories. Because you've got the category of groups in the category of rings. At least I think that's how category works. I haven't actually taken a category theory class, but I'm pretty sure that's how. I'm pretty sure it's all just the same, and you go to category theory and you're like, wow, this everything just is the same as everything else, sort of. So, anyways, I claim that R mod I is Noetherian. So to prove this, let phi from R to R prime be any this is going to be a preliminary result. So let phi from R to R prime be any ring homomorphism, and I prime and R prime an ideal. I claim that phi inverse of I prime, which we will define to be equal to I, is an ideal of R. This is a pretty standard fact about ring homomorphisms, and it might be something that's just so basic that you don't really need to, like your teacher understands that, oh, this is something that you're supposed to know, this is something we talked about in class, we don't even need to prove it. But let's do it. To see this, note that the zero element of R is in phi inverse of 0 R prime. Right, because phi is a homomorphism, and so it sends the 0 in R to the 0 in R prime, and so it's contained in the inverse image of the 0 in R prime, but the inverse image is precisely I. So there's that. So given A and B and I, we know that phi of A and phi of B are in I prime. So phi of A plus B is in I prime, because phi of A plus B equals phi of A plus phi of B, which is a sum of two elements of an ideal, and thus is contained in the ideal. So A plus B is in I. Okay, now given A and I and R and R, phi of R is in R prime, so phi of A times phi of R is in I prime, because I prime is closed under, you take an element in I prime and you multiply by any element of the ring R prime and you stay in I prime. And this is a homomorphism of rings, and so phi of AR is in I prime, and thus AR is in I. Hence, inverse images of ideals under ring homomorphisms are ideals. Okay, so let's see, do I want to start a new paragraph? Sure, why not? So now, we're going to call it I1 bar to I2 bar. Rather, no. We'll start with that. Let I1 bar subset I2 bar subset blah 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 be a chain of ideals in, I wrote R mod I. I mean R prime, no. Where are we? This is going to be R mod I. Remember, R is the ring that we're starting with, and I is just some ideal. And so we're looking at the quotient ring, and we're considering a chain in the quotient ring. And we want to prove that the chain in the quotient ring terminates. But we know that that chains in the ring I terminate. Let phi from R to R mod I be the natural homomorphism, which sends an element R to the coset R plus I. And then for all I, let fantastic notation, let I sub I be phi inverse of I bar. See here. Now the fact that I is contained in I plus 1 implies that phi inverse of I is contained in phi inverse of I plus 1. Now, yeah, because this is inverse images or functions don't behave well under, like, you take the inverse image of one element and you could get a whole set. So you immediately think, okay, taking the inverse image is bad. But actually, inverse images are really nice under operations like inclusion and things like that. And these things come up a lot, particularly in measure theory. You start to realize, inverse images are nice. Actually, no, I don't think it's just measure theory. I think, like, in measure theory, it's like more back to categories. I think the measurable functions are the morphisms, and a measurable function means that the inverse image of any measurable set in the in the codomain is a measurable function in the domain. No, measurable set. Inverse image of any measurable set in the codomain under this function is measurable in the domain. And I think there's a lot of stuff about pullbacks that comes up in category theory. Things involving, like, you take a word and you add co to it and then it becomes something like different, or something reversing arrows. I don't know. I've heard people talk about category theory, but I've never really understood what they're talking about. So anyways, this happens, and this is nice. So I1 contained in I2 is a chain of ideals in R. That was no good. Of ideals in R. Since R is Noetherian, there exists a n. This n does not have a dot in it, and that means it's a natural number and not just abbreviation for Noetherian. And this is such that for all n greater than or equal to n, in is equal to in. Then for all n greater than or, i.e. that the chain terminates because it's Noetherian. Then for all n equal to n, this pushes forward to the other chain. And so this chain should probably include at least one more element so that you see the pattern. Terminates. Or rather, I think stabilizes is better, because it doesn't necessarily terminate. It will eventually stabilize. It will eventually, everything will be the same, and so it's like, even though it's not, it hasn't stopped going. It just has stopped changing, and so it stabilizes. This holds for every ideal chain in R mod I, and thus R mod I is Noetherian. Hence, if R, here I'm going to write this in really concise notation. Hence, R Noetherian and I ideal in R implies R mod I is Noetherian. And there we go. We've completed this proof.